Hi, this is an example problem from Chapter 31, the energetics of decaying radium. Pause for a moment to read the question. So we're going to start here just by writing the reaction equation for the radioactive decay of radium-226 by alpha emission. So we're going to start with the parent there, the radium 226, and I don't remember how many protons radium has. Let's go look it up real quick. Radium. There it is, 88. Z equals 88 for radium. And that's going to emit an alpha particle. So we're going to get a helium nucleus, and that is 2 protons, 2 neutrons, and so we need to balance these. This is going to be 226 minus 4, going to be 222. And balance the number of protons, the charge, 88 minus 2, going to give us 86. And let's identify what that particle is by looking at the periodic table. Radon, 86. All right, part B. Calculate the energy released in mega electron volts in the alpha decay of radium-226 atom. Use the following masses. All right, how do we always calculate energy of nuclear reactions? Let's go back to our notes here. We call the energy Q, the energy released or consumed in the reaction, a Q value, and it's going to be the difference in the masses on the two sides of the equation. The reactants, what you start with, minus the products, what you end with, times C squared. This way, if you have less mass in the products, you have energy that has been released because the products have less mass. That mass has been converted into energy Q. On the other hand, if you get a negative value of Q, you're going to have a larger amount of mass in the reactants than you did in the products. That means that it takes energy to make the products which have more mass. Now, for a spontaneous reaction like this radioactive decay, you're always going to have a positive Q value because it's spontaneously reacting to release energy. All right, so we've got our equation there, and simply we need to just remember that these on this side here, this is the reactants, what you start with. And on the other side over here, these are the products, what you end with after the reaction. So we're going to calculate the mass of the reactants. So in this case, we're going to have a single thing here just for the radium. It's going to be 226.025402 atomic mass units U. Again, super important, critical. You use all the digits. You can look these up in the back of the book. In the back matter, they have a list of a bunch of the masses if you need to look them up for a particular nuclear species. All right, that's it for the reactants. Now we're going to do the products. We've got 2 products. We need to add those masses together to get the total mass of the product. So let's start with the radon, 222.017571. Good to double check those numbers and make sure you got them all right. We've also got a helium nucleus, the alpha particle, 4.002602 atomic mass units. Putting this into the calculator, this gives a value, I forgot to multiply by C squared. This gives a value of 0.005229 U times C squared. And now what we're going to do, as usual, we're going to convert this to MeV. The conversion factor for MeV here is 931.5 MeV per C squared divided by U. And as usual, the C squareds cancel out. The U's cancel out. We're left with MeV, what comes out to 4.87 mega electron volts of energy was released in this reaction. And of course it's released because there is less mass in the products and the reactants, and therefore that mass that was lost was converted into this energy, 4.87 MeV. Now it's interesting to ask what happens to that energy. Typically it goes into kinetic energy of the products. So the radon, the alpha particle come blasting out with lots of energy, a lot of kinetic energy. Interestingly, in this reaction, the momentum has also got to be conserved here. And it turns out that because of that, if we write the kinetic energy in terms of the momentum, we'll see that the particle with the smallest amount of mass is going to end up having the greatest kinetic energy. It's going to be ejected out at a very high speed. And so they actually used to use this, and they still do, as a way of having firing particles, alpha particles, for example. They used a radioactive source like this in Rutherford's gold foil experiment to fire alpha particles and understand the form of the nucleus back in the day.